Hello everyone, my name is Craig Otto. This is a supplemental video for Operational Excellence Technology. And one of the things I want to go through today is capability. This particular example that I have here is just a run of data. We have, you see the dimension is, the nominal is 1 plus or minus 3/10 there. And then we have a set of data. And one of the things we need to do for capability is we need a mean, a standard deviation, and spec limits. And let me zoom in here so we can kind of really dial in. The first thing, the mean, that's pretty straightforward. You can see my formula here. It's just the average of my data. And let's see, I got it highlighted here. And the next one, depending on what type of capability analysis you want to do, you need a certain type of standard deviation. The first one, if you're trying to find CP, which is short-term capability, that is denoted by S sub x, and sometimes you might see it as R bar divided by D2. But the bottom line is it's short-term. It's known as sampled standard deviation, and you can see the Excel formula there, STD EVA for sample standard deviation. And in this particular example, it's 4 thousandths. The population standard deviation, this particular one, very similar, but this is more denoted as long-term variation in the process. And you can see it's 4 thousandths even. So these two pretty much are identical. A lot of times, though, you'll see actually the population standard deviation be a little bit larger because it is the population and it's not estimated. So, and it's also known as more of a long-term capability. So you just got to know what you're dealing with. For the sample standard deviation, or S sub x, you're dealing with CP and CPK. For the long term, where you see a sigma here, that would be for PP or PPK. Okay. Other than that, the formulas are identical, so it's just a matter of knowing which standard deviation to use. So with that, we'll go ahead and actually get into calculating it. Our upper spec limit also is 1.03. That's just your 1 plus your 0.03. And then your lower spec is 1 minus that, the 0.97. Okay, so getting into the actual outputs here, you can see our formula for CP is actually upper spec limit minus lower spec limit divided by 6 times your S sub x. So if I do that in Excel here, this little formula, kind of see here, I just take my F5. F5 is right here, my upper spec limit, so 1.03, and I subtract F6, which is 0.97. I divide that by 6 times my standard deviation. You can see I'm using S sub x because it's CP. And that's what you get here, 2.49. In terms of CP, you can actually have any number that's greater than 0. So basically, to tell whether a process is capable or not, you'll want something that's at least greater than 1, and a lot of times industry standard is greater than 1.33. Okay, what that means is if it's greater than 1.33, the probability of it producing a good part consistently is very good. If it's less than that, then you're getting into the case where over time you'll probably be producing bad product. Okay, now I also want to get into CPK, which CPK has 2 parts to the formula. One is you calculate a CP lower and a CP upper. And the way that you do that is you have to get your mean involved. So for CP, you don't use a mean. But for CPK, you have to. So mean minus your lower spec limit. So for us, our mean is this right here, 0.9816. You subtract out your F6, which is your lower spec limit, and then divide that 3 times, again, your S sub x. 3 times S sub x. Okay, and that formula equates to 0.96. Let's just sit tight with that for now. Let's go to the CP upper. CP upper, the reason it's called lower and upper is you're just subtracting the mean from either the lower or the upper from the mean for the upper. Okay, so upper spec limit minus your mean, come in here. So it's upper spec limit 1.03 minus 0.98 divided by 3 times your standard deviation, and that's 4.01. Okay, now CPK takes both of those formulas, CPL and CPU, and says, what's the minimum value between those? So the minimum value is your CPL, that's 0.96. Okay, so CPK actually, I mentioned CP is going to be greater than 0 to infinity. In the case of the CPK, you could actually have anything from negative infinity all the way to positive infinity. And I'll give a couple of examples here in the future to kind of explain what happens when your CPK is negative, what happens when it's 0, what happens when it's positive, and at what point do you consider it capable. This particular process, your process is not, um, it's capable based on the CP. So what it tells me is your process is not centered, because in order for it to produce consistent product, you need it to be above 1.33. We're at 0.96. So it's not terrible, but it's not good either. That's short-term capability. Long-term capability, everything I just did with CPK, it's the same thing, only instead of multiplying by S sub x, you multiply by sigma, this 0.004. Okay, so everything else is the exact same. You can see the numbers come out to almost, the exact same numbers. Your PPK ends up being 0.96, similar to your CPK, which was 0.96, and your PP value was 2.5, slightly higher. Again, normally it's the reverse of that. Normally your PPK and PP values are less than CP. It just so happened this example, it didn't work out that way. And because your PP and PPK are normally lower, the magic number for that is 1 instead of 1.33. Okay. And again, these magic numbers, it depends on the industry. Like in the medical industry, that's actually 2.0 for CP and CPK, and 1.5 for PP and PPK. 1.33 and 1 are typical. You'll see those in automotive and several other industries. So it just kind of depends on what type of product you're making and how important it is, how critical the dimensions are. But for the purposes of this class, we'll just go with 1.33 for CP and CPK and 1 for PP and PPK. So let me give you some visuals of what this actually means. Let's run through an example here. First, let's talk about just pure capability, CP and PP. So in this particular example, I'm going to give you a upper spec limit of 17, a lower spec limit of 5, and I'm going to give you a standard deviation of 2. Okay? So I'm going to jump over here. I'm going to plug in my standard deviation of 2. Here you can see I got my distribution, my bell curve, and my upper spec limit and my lower spec limit is in red. So anywhere where this product falls, this blue part, that falls in red, that means it's not conforming. Now, I have it currently centered in the process, and that's fine. Actually, with CP and PP, you're not even looking at whether it's centered or not. You're just trying to consider how is it capable or not. If it was perfectly centered, would it be capable? That type of thing. So in this case, 11 and a standard deviation of 2, it looks like it's almost right at the bare minimum of being capable. In other words, these little tails sticking out down here is what you're producing bad. So that's not terrible. Let's go back to what this gives us is upper spec limit 17 minus 5. There's your 12 divided by 6 times your standard deviation of 2 is 12. So 12 divided by 12 is 1. So I would say that it's potentially capable. And when your CP and PP are 1, that means you can fit your 6 sigma or your bell curve within right on the spec limit. So plus or minus 3 sigma. So right here, minus 3 sigma is 5, plus 3 sigma is 5 or 17. And the way that you get that is 11. And if you want to go 3 standard deviations to the right, it's 3 times 2, which is 6. So 11 plus 6, 17. So that's perfect. And 11 minus 3 times 2, which is 6. So 11 minus 6 is 5. That means you're perfectly at 1. And that's why it comes out to 1, the value of 1. Now let's do the same thing, only let's make our distribution 2. Okay? So if my sigma is 1, I take 17 minus 5, which is 12, divided by 6 times 1. It comes out to 2. And kind of what that means is you could fit 2 distributions within that spec limit. Let me give you an example. So my standard deviation was 1. See how it tightened up my curve? See, now it's pretty obvious that you can make all good product. And that's why the CP and PP is 2. But let me also show you, if I go and let's make this 8, what it really means is I could even fit up to 2 of those distributions within the spec limit. Does that make sense? So the same distribution can fit 2 times. That's why the value comes out to 2. Okay? And that's a very capable process. Whether it's centered or not, it's very capable. All right? The next example, I'm going to change the standard deviation to 3. Okay? So it'll be 17 minus 5, which is your 12, divided by 6 times your 3 standard deviations, 18. 12 divided by 18 is 0.666. That is not capable because it's less than the 1.33 or 1, depending on if you're talking about PP or CP. Okay? So that is not capable. Let's see if we can see why. So if I come in here, clear out my data, my standard deviation was 3. And even if it was perfectly centered at 11, you can see there's still, look at my tails here. I'm producing bad product potentially. So that's why this value of 0.667, that's why it's not capable. Okay? So that's your examples of CP and PP. Let's also go through CPK and PPK. I'm not going to delineate which one I'm using. Like I said, they're the same thing. It's just depending on what standard deviation you use, whether you use sample or population. Okay? Sample for CPK, which is known as short-term capability. Long-term capability is noted as your sigma or your population standard deviation. Okay? So with that, let's get started. Again, CPK and PPK have a lower calculation and an upper calculation. And then the actual value of it is just the minimum of those 2 values. Okay? So in this first example, I'm going to use a mean of 6, standard deviation of 1, same spec limits that we had before. Okay? So what we'll do for PPK lower, it's actually your mean, which is 6, minus 5, which is your lower spec limit, divided by 3 times your standard deviation. Okay? And that's what that formula is. Plug the number in and you get 0.333. PPK upper is basically your upper spec limit minus your mean. So 17 minus 6 divided by 3 times 1. And that comes out to your 3.67. Okay? And the PPK is the minimum of that. So 0.3333 is not a good CPK or PPK. But what it does tell you, because that it's positive, the average is within the spec, but you're still not consistently producing good product, okay? So let's go ahead and map this out. So 6 and 1 is our mean and standard deviation. Oops. Okay, so this is what that looks like. This PPK is 0.333. And the reason it is your tail is out of spec here, actually a large portion of it. And I mentioned your average, which is the top of this bell, is within spec, right? Because it's positive. Just remember that. If it's positive, that means it's at least within spec, okay? But you are producing bad product because you're less than the 1 or 1.33, okay? And this will start making sense as we go on here. What if our mean was 4 and 1? So let's dump that in. 4 and 1. Now you can see my mean is actually out of spec. And actually we're producing more bad product than good, according to our curve. So let's see how the numbers translate. Okay, so you take your 4, which is your average, subtract your lower spec limit, which is 5. So 4 minus 5 is a negative 1 divided by 3. That's why you got a negative 0.3333. And your PPK upper, 17 minus 4 divided by 3, is 4.33. Now, that 4.33 is a good number. Why is it so high? Well, what it's saying is your average compared to your upper spec limit, which is all the way across, your probability of producing bad products is not that good. In other words, it's not going out of the upper spec limit. It's not probable. That's why the number's so high. That's why this number's so high. That's a good PP or PKU. But the formula says you got to use the minimum value, so the worst case. So that's why we're using that minus 0.33, because we're producing bad product out on the left side of that lower spec limit. Okay, so positive value means that it's within spec. Negative value means that it is out of spec, the average, that is, I'm talking about, the average. And then what does it mean when it's 0? What happens when the mean is actually, or the PK is actually at 0? What does that mean? Well, it means that my mean or my average is the exact same thing as my lower spec. Does that make sense? So when you do the math, my mean minus my lower spec, 5 minus 5 is 0. That's why you get a 0 here. And then again, you do the same calculation for upper. It comes out to 4, which is good. It's just you got to use the minimum value. So minimum value is 0. Okay? So it means that my average is right on the spec. Negative means I'm out of spec. My average is out of spec. Positive means my average within spec. 0 means I'm right on the spec. Depending on, and the way that you tell which spec you're right on, if your lower is 0, then you're on your lower spec. If your upper is 0, then you're on the upper spec limit. Okay? Let's do some more crunching here. Let's say our mean is 11. So now our process is centered and our standard deviation is 3. So 11 and 3. Okay? You can see just without even doing the calculation, we're centered, but we got some tails sticking out over here. We're producing bad products. So my guess is we're going to have a CP value that's positive because my mean is within the spec, but it's going to be less than 1 because I got my tail sticking out in the spec limits or out of spec conditions. So let's do the math though. We come in here, we take 11 minus the 5 for the lower, divided by 3 times 3. That comes out to your 6 divided by 9. Do the same thing for upper, 17 minus 11. 6 divided by 3 times 3 is 9. So 0.6667. So these two values are the exact same thing. When that happens, that means your process is centered. Okay. Minimum value of those, obviously either one. So what that means is the problem is variation. It's not that your process isn't centered. The problem is that it's too spread out. Okay. And then this last one, we're going to do one where the process will be centered and the variation will be low, so it'll be a good process. Okay. We're going to go from a mean of 11, which is what it was last time, but this time we're going to reduce the variation to 1. So let's see what that looks like before we run the numbers. Okay. This looks very good. You've got none of the tails sticking out in the out of spec condition. Your average is right in the center of the spec limit. So this should give us a very good number. Usually when it's like this, you'll see something like 2 or above for the capability number. Okay, so 11 minus 5 divided by 3 ends up to be 2. So 6 divided by 3 is 2. Same thing from the other perspective, taking the upper spec limit minus the average, divided by 3 is 2. The minimum value between those is 2. And again, process is centered, variation is low. This is a good process. Okay? Hopefully that clears some things up for everyone and makes a little bit more sense of capability. It's really not that difficult once you kind of get the hang of it. It's just understanding what the numbers are saying. So if you have any other questions, please don't be afraid to ask on the discussion forum, and have a good day.